All right, let's start from the top. So that's me. Went over some context. Um, it is generally a lot cheaper for us to throw in a CPU into things to emulate simple logic functions, and to just let a CPU control things instead of being dedicated hardware. Since there's more complexity, and a CPU is a general purpose it's a general computing device, there's less control of what possible states there are. So there's less control of risk, thus we are more insecure. I mentioned Thomas Dillon's presentation, and as mentioned last time, why is state harmful for one-time pads? Because if there is pad reuse or it's not immediately destroyed after use, the information theoretic security properties of one-time pads will break. So now we're talking about methods to backdoor hardware. There are two main strategies to backdooring hardware. One is considered active tampering, and the other is data logging. Active tampering can weaken security, as you can see, by injecting periodic signals or like injecting garbage data, and can also cause denial of service if there are fail safes in place, e.g., like bad signals to cause uh random monitor to say, oh, um, I'm getting too much garbage data. I will just stop spitting out data. The other is data logging, which, like mentioned as before, keeps state and it breaks the information theoretic security property of one-time pads. There are three main methods of backdooring. One is replacement of components, second is malicious modification to silicon, and third is embedding malicious like add-on components into silicon. You can basically replace a logic gate, FPGA or CPLD with microcontroller. What people realize nowadays, it is quite feasible considering we have microcontrollers with peripherals that have deterministic and fast timing. So it can basically emulate logic gates, FPGAs, or CPLDs. Two examples are the PyPico and the BeagleBone Black. If used in the data path of a secure computing base, it can be used for both tampering and logging. If used in a control path, it can be used with like active tampering. Uh, for malicious modification, it's quite scary. There are like you can do open transistor trojans. Those trojans can trigger malicious or incorrect states during runtime, and proof of concept has been done. Researchers like in like 2012, and researchers discovered like a dopant level backdoor in, I think, an FPGA or something. Also design level tampers, you can create a malicious design in the Illinois malicious processor model, and basically like in their attack they use the shadow cache to trigger malicious code execution. This method can be used to like buffer and log data for use in a one-time pad computation system. And then the last, which is honestly probably the scariest part, is you can easily embed malicious electronics into like off-the-shelf components. It is I've consulted with a friend of mine, and you can like you can basically tap the bond wires of a comparator with microcontroller and log the data output. So yeah, also you can embed like a RC oscillator into op amp to inject a malicious signal if you use op amps or analog computers to do your computation. And for individual transistors, you can actually like it is possible to embed like a programmable like a PMC, which is a non-volatile memory storage element at the MOSFET at the transistor's gate, and it like basically after it depowers, you can log the last state the gate was in. So hardware trojans can be used for both tampering and data logging, as they can be present in both the control path and data path of one-time systems. So I've been working on a project which is to generate random paths and like compute paths and hopefully immune or highly resistant to backdoors. Third model, the intended users are basically people who do not have access to specialized equipment and who need in information theoretics secure assurance in data confidentiality when using pads, and also high assurance in that the encryption decryption process is as intended and there's no logging or backdooring. Yeah, basically, and also it's basically designed to go up against a nation state. Physical attacks and rubber hole attacks are all scope because if if you people usually give up secrets under duress, probably. Adversary capabilities, your government entities can basically swap up component chip to you, and they can possibly flood the supply chain and market with changed or backdoored components. They can physically raid users because, well, law enforcement, and there are basically they can pull off advanced attacks like embedding the PMC onto the gate of a individual transistor, also rubber holes attacks. So project requirements, ideally the pad calculator can mitigate the outlying attacks. It can be easily verified by a user without using specialized tools like scopes or pulse generators. It can be built using diverse but compatible components. Like, let's say a single a 2N 7002 MOSFET can be swapped out for another NMOS, and then you can use components sourced from diverse sources. So no one single source targeted and backdoored. Essentially, it would increase the difficulty of backdooring all available components, and also be very easy for someone to pull off an attack like this, and also easily assembled. So basically, a user doesn't need to solder down something transistors. Mitigation strategies to the aforementioned backdoors. General guidelines: reduce the complexity of design, and reduce reliance on component toolsets, precision components or specialized components. But I mean, FPGAs, specialized components like FPGAs, are usually not able to be swapped out from a design once integrated. So if a design uses it, and certain government or high level entities decide to target the design, you don't have a second source you can swap out to. And also, considering mentioned that don't use integrated circuits, considering you can bond a microcontroller in the same package as a comparator, and also use a physically inspectable. You can select channels. I'll just let you read it. Basically, there's acoustic, current, emissions, and thermal side channel you can mitigate using the thing. Design for untrustworthiness, that is the implementation stage. That's for later. Here are some example suggestions. Schmidt triggers, basically a window function. If it's above or below a certain thing, it can trigger. Transistor gates usually if are not Schmidt trigger, that means if you have a voltage in the middle, they glitch out. For Schmidt triggers, that won't happen. ECL is current steering, so there's instead of switching on and off, it constantly is on, but just direct current, so there's noise and stuff. And also have a jig to test individual components. So hopefully, if entities decide to pull off the PMC, embed a programmable metallization cell in a transistor, you can detect it. Some progress reports for the project. The implementation is completely done, and previously I mentioned I proposed a analog solution. However, considering that I discovered a feasible method to backdoor the comparators required for an analog solution, we're not doing that. Hardest challenge not solved yet, because trying to transfer the randomly generated pads in the paper is going to be quite noisy if you're using solenoids to punch stuff on tape, or also I'm not that good at mechanical design. That's a problem. The physical gauge can have a few ideas, but I'm still choosing on a logic family to use, likely CMOS, but could do bipolar like ECL for sound resistance. And here's how we, so here's a rough draft, high level design of the random number generator works. Basically, you have two diodes that generate noise. You take the voltage difference between them. If the voltage, let's say diode A's voltage is higher than diode B, the comparator outputs a 1, vice versa, it outputs a 0. That's how we generate the bits. I'm not too sure if this can eliminate like auto correlation in the signal, like basically correlation to itself. I'm not sure. Still asking, because correlation bad for like unpredictability of random bits. So for the random bit out, we feed it into a Neumann debiasing circuit. I have tested it using like Icarus Verilog. The circuit, it basically what a von Neumann debiaser does is it takes this circuit takes two random bits in serially, and if they are different, it outputs the first bit, and then you can just feed it to like a 0 in parallel out 8-bit shift register to drive like whatever you use to interface with the real world to transfer the data onto like physical pads. Yeah, here are the references for stuff. Sorry, I'm not exactly too prepared. If you're interested, I can elaborate on some of the previous details on the methods of like backdooring. Suppose, where is it? Yes, basically these things. And I think the comparator thing I can give. I can probably explain it in detail during the discussion, but otherwise, yeah, that is the presentation.